Okay, hi there. In this video, I'm going to show you how to determine the expression for the rotational inertia of a hollow cylinder about its axis of symmetry. And we're going to use the standard definition for rotational inertia as an integral. And we've got a picture here of our hollow cylinder. The axis of symmetry is going to run right through the middle of it. Okay. And the trick that we're going to think about to do this integral is the idea that you can build up the cylinder by sleeves which get larger and larger. Their diameters get larger and larger. And you make the sleeves like really, really thin. And so the analogy that we can think about is a toilet paper roll because the whole roll obviously has thickness to it, right? But that thickness is made up of probably thousands of different, like, circles that are made up of the individual, thickness of the paper on the roll. So think in terms of sleeves here. The sleeves are going to be kind of like just an individual circle of paper going around, and that sleeve thickness is going to be quite small. All right, so let's start off by seeing how we can simplify this dm, because again, the integral cannot really be solved in this form, so we're going to have to substitute and get rid of that dm. So what I'm going to do is I'm going to remind myself that mass is equal to density times volume. We're going to assume that density is constant. Okay, like it would be for a roll of toilet paper or for a solid cylinder made out of wood or anything like that. So we're going to assume that the density is constant. Rho is the symbol. I'm going to take the derivatives here. We'll write this in differential form. And so I'll have the mass element dm in my integral. That's going to be this. But I'm going to end up substituting rho times dv. Okay. Now dv is going to literally be the volume of one sleeve. Okay. And remember, when I'm talking about the sleeve, I'm talking about this really thin circle of paper that is making up part of the roll. Okay? So what we need to do is to say, well, how the heck would you come up with the volume of a single, circle of paper that has a radius which you can make vary, so it can have a radius of r, lowercase r. It's going to have a height of L, and it's going to have a thickness which is really, really thin, and we're going to call that dr. Okay. And the answer to that, I'm just going to write this expression down. I'm going to say that, let's see if this makes sense. So I'm going to say dm is equal to rho times 2 pi r. That would be the circumference of the sleeve, 2 pi r. Multiplied by dr, that's going to be the thickness. Now guys, I hope you can see now that if I take the circumference, which is a length, and I multiply by a thickness, which is a length, I'm going to get an area. That's the area of the edge of that sleeve. So in order to convert that into a volume, the last thing I would multiply it by would be the length, or in this case the height of the cylinder. And that is basically the substitution that we're going to make here. Okay. So you might have to ponder that a little bit, but this is the hard part of it. Okay, so now let's go and substitute it in. So instead of dm, I'm going to actually write all this stuff. I'm going to write rho times 2 pi r times dr times L. And I want to remind you that r is actually a variable here. if you look up in our figure, I'm going to circle it, and I'm going to write the word varies, because that R, it's going to vary, meaning it's going to start off at R1 and it's going to go all the way out to R2. So in the integral itself, this is going to be our variable of integration. So R is a variable. Now, what is not variable would be the inside radius, which I'm going to make on an endpoint, and the outside radius, which I'll make the outer endpoint. Those are fixed values. You might be given those in a problem. So what we have now is an integral, which is not difficult to solve, and the variable of integration is R. So let's proceed. I'm going to take all the constants out. So rho, 2 pi, L. And I will be left with R cubed from R1 to R2. Okay, and that's a pretty easy integral to solve. I'm just going to continue here. That brings 1/4 R to the 4th. And that's evaluated from R1 to R2. Okay, so it's a very simple integral to do. That's going to give us 2 times a quarter is 1/2 rho pi L. And that's going to be multiplied by R2 to the 4th minus R1 to the 4th. Okay, I'm going to use a little bit of algebra here. I've got a difference of 2 terms to the 4th. That's going to be the same thing as the following. So it's R2 plus R1 squared, R2 squared minus R1 squared. You can try that to verify it. It's good practice with algebra. All right, these two things should give you what's up above. Okay, so now we've got an expression here, which is good. This expression by itself, actually, you could probably stop here and say, well, I've got it now. I can calculate the rotational inertia if I know the density in the two radiuses. The thing that's going to be a little bit simpler is if we could actually, instead of talking about the density here, if we could talk about mass. So I'm going to say the total mass of our cylinder, of our hollow cylinder, could be determined by taking the density, multiplying it by the area of the top part. So it would be like this area, right? So pi times r squared is going to give you that area. And this is not the sleeve, by the way. This is the whole thing. Okay. So you're going to get that area, and then you're going to multiply by L to get the volume of that thing. So rho times pi times this stuff times L is going to be the total mass. Okay? You might have to think about that a little bit. But that can actually kick out a lot of things here, and it will leave you with a much simpler expression for the rotational inertia of the cylinder. Okay? And so that's going to be our thing. So this is total mass here. So you got to really keep track of your r's. Of little r is a variable in this process. Big r's are actually constants. You also have to keep track of the fact that m here is the total mass of the cylinder, and most of the time you know that from a problem. All right, so that's it. I'm just going to show you how this kind of can boil down to two nice results that should be familiar to you. Number one, what happens if you have a solid disk? And number two, what happens if you have a hoop? In fact, this equation is going to reduce to familiar equations pretty easily. If you have a solid disk, that's like saying that R1 is equal to 0. If R1 is equal to 0, then the mass is spread out over the inside of the entire disk, and you're left with 1/2 m total times R2 squared. And that is the formula that we've been using for the rotational inertia of a solid disk. So that should look familiar. Hey, that's cool. For the hoop, in the case of a hoop, you would be saying that the R1 is equal to the R2. So all the mass is on the outer edge. And in that case, when you add these two things together, I hope you can see that this becomes 1/2 m times R squared plus R squared. And of course that becomes 2R squared, which cancels the 1/2. And you get the familiar mr squared that we've been using for hoops. So this formula actually is kind of nice because it simplifies into two very useful formulas that we've used in a lot of problems. Okay, so hopefully that makes sense. I would say really review the idea of the sleeve as being the mass element. That's the key part of this problem, and otherwise the steps are evaluating this integral. All right, have fun then.